for introducing me and giving me the opportunity. So I think this is my second session in the series of this wonderful FDP program. Um so for today's session, there is agenda regarding where I will be talking about some parallel algorithms, then generic workflow of the any program on the systems from like a serial as well as the parallel one. Then finally we'll touch upon some of the optimization aspects, right? So let's start on the session. So as of now, in the in this current FDP program, you know that some of the parallel program models, right, starting from OpenMP, MPI, then you may have also been touched upon some of the aspects of the CUDA, right? So also you have the fair understanding of the underlying architecture, right, where and in which scenario these parallel program models will work upon, right? But before like starting any program to write, okay, before choosing any method to solve your big problem, what basic understanding one should have, those aspects we will be trying to understand, and we'll try to touch upon the things regarding it, right? So as I always assume that, okay, and I think that the parallel programming is an art of management basically. So the syntax of the different program models is one aspect, but in which scenario and in what uh, task those program models fit into, and if you have the bigger problem, how one can start to solve that particular problem with these underlying like whatever the tools and technologies with respect to the different models are available with. So that is the big question, right? And in this particular session we will try to understand those aspects, right? So generally when let's start from like very basic thing, right? So generally when we have any program with us, traditionally you may be writing your programs either in the C, either in the Python, okay, or any other program models which you wish, right? So here just try to understand this just take a very simple C program where we are printing some simple text, right? And when we try to compile that program and when we run it, so at the back end, basically how that gets executed. So the current systems which are there into your like premises, or maybe the HPC systems like a param systems where you may have the access of it for the FDP and those things, there may be the scenario. But just try to understand one thing, in your labs as well, or the systems which you are working like laptops or maybe even phones as well. So there are systems like a multi-core kind of processor are present on your system, right? But when you try to write any program, so the question is that, are you really using those underlying cores efficiently? So basically when the traditional program, when it try to run, and actually it uses only a single core of system. So it means that the underlying remaining cores on your system at that moment, those are like idle. So it means in some way we are underutilizing the cores, right? And that's why we need to have understanding, and we need to have the skill of writing the parallel programs. So the very first thing is that, because nowadays the resources are available with us, okay, and when the resources are available with us, we should use those optimally. And in that journey itself, as of now you have studied some of the parallel programming models like MPI, OpenMP, or the CUDA and those, so just to optimize those resources in the programmatic essence, right? So then as I had mentioned earlier, okay, so there is a need of parallel program model because you may not be utilizing your systems or the infrastructure optimally. So as I had mentioned, okay, why parallel program models and these are necessary, there are like multiple reasons for it, right? So the one is like to utilize the resources efficiently, another is like to get the optimal performance, because if you have the resources but you are not using it, then certainly you are losing the performance, right? So your first target is to use those resources to get the maximum performance for your program. Then another one is like a scalability. So if you have the today you have some resources, your code should be like such a scalable that in future if a similar kind of systems come into the picture, without any like much modification, your code should scale, and scale means that code should utilize all those resources as well, to give you the problem once again in a less time as compared to the previous, right? Then certainly in order to like calculate the complex problems, to solve the complex problems, okay, then like big data processing and concurrency and responsiveness, these are like some of the aspects, okay, or the challenges where we need to uh, take parallel program models into consideration to solve upon, right? So as of now you have seen it, I'm just like in a couple of minutes I will just recap those things which you have learned as of now and the different scenarios, just to make you on the pace, right? So when we had talked about the parallel program models, okay, there is a concept called a shared memory model, distributed memory model, and accelerated computing system. So I assume that you have now a good knowledge of at least a sense of these models, right? And when like in a practical sense, when we look into where this particular program models fits into the current year of the advanced systems, then when we look for the like a shared memory system where openmp systems like program models comes into picture, right? And when we try to talk about the distributed kind of systems where multiple nodes are connected with some network, okay, then the scenario comes into picture, okay, called as a distributed memory system, and in which the mpi comes into picture, right? And the third scenario is like if you have an accelerated card with you, okay, then the program models which comes into picture is nothing but a CUDA, right? And if you want to use this mpi plus openmp, then the model which like OpenMP and MPI, then if we are using and simultaneously, then we generally term it as the hybrid kind of program model, right? So I assume that okay, you have the like a pretty much good understanding of these things. I have not talked in detail about it because I assume that you have already studied it, right? So now let's assume that now you have a system with multi-core kind of system, or a system with having the uh, the accelerated nodes with you. So if you have the system and you know some of the pair program models, so what is your target in the sense, right? So if you have the big system but you somehow you are not able to utilize it properly, just take an example. If you have like a very good horse, I always give this example, right? So just to relate the things, if you have the good horse with you but you are not able to ride that horse, then there is a wastage of the resources which are available with you, right? So now you need to develop a skill set where you should be able to effectively drive it, right? So now when you are ready to, let's say, learning the things, now when it comes to a real life problem, right? So whatever the domain which you may be working upon, so there may be the different problems from the different domains maybe with you, right? So though you have the knowledge, let's say, of MPI, OpenMP, CUDA, and you know like that there is the system as well. Now when it comes to a real applicability of that particular models or the knowledge, then some questions comes into the picture, like from where I should start. Let's say you are working in physics domain, or maybe a chemistry, or maybe like CFD, or maybe an like data science domain, right? So the first question comes into picture, that from where I should start. So just to answer that question, very first thing we need to do is to identify our relevant problem accurately and optimally, right? And once you identify that particular problem, then there another like steps come into the picture, right? And what are those steps? Okay, we are going to discuss those things in coming upcoming slides, right? So there should not be a scenario, right, where you got a problem, you identify the problem, and you just start writing the program because you know you have the knowledge of the MPA, OpenMP, or maybe the CUDA. So that is not a good and proper approach, basically, right? So before starting the problem, like solving the problem, one should have, as I was mentioning, parallel programming is nothing but like a more managerial kind of skill. It means that you should properly understand the problem, you should have a clear cut idea of the distribution of the workload of your problem, right? And once you have the distribution of the workload with you, you should be able to connect all those dots efficiently so that you achieve the two aspects. One is efficiency or the performance for your problem, and another one is accuracy, maintaining the accuracy of the results, right? So those are the aspects which you need to consider. And how, if you have the problem with you, and how one can start with, we'll try to see some of the aspects. So on that journey, there are like, in standard perspective, traditionally there are uh, different, actually the approaches, basically I can refer it as, there are different approaches to solve or design an algorithms for going for a parallelism, right? And here we'll try to address some of them. So before I will be touching one by one, algorithms, one thing always remember, before writing or decomposing any problem for implementing it into a parallel uh, scenario, that one aspect is, you should clearly identify, okay, where my problem consists of components which are computationally independent to each other. So if your problem consists of a components, okay, which can run parallelly without affecting the accuracy of system, in that scenario only you will be able to write parallel programs. Otherwise, what will happen, your accuracy will hamper and there will be no use of it. So the very first thing you need to identify is that, okay, I have one problem with me, a big problem. Now the next step comes into picture, that just try to decompose that problem and try to identify whether there is any independent component present into my workflow. So when you sure that, okay, I have some of the parts of my program or my problem, okay, where I can parallelly work upon, then you just identify those problems and then try to implement models, okay, the algorithms, to have the parallel processing on it, right? So I hope whatever I mean to say, I'm able to convey you, right? So now once you are ready with your problem, and as well as some of the components, okay, no, I can, now I have the fair understanding of the components and subcomponents of my problem, then now next comes into picture, like which methodology I should follow, right? So traditionally, basically, like there are different methods, right? And generic methods are there, right? So we'll try to touch upon like in your particular case which things may be suitable. Those things will come into picture, right? So when we talk about the parallel algorithm, basically this is just nothing but a process where we mean to utilize our underlying multiple cores or the whatever resources with us, right? So traditionally there are like different methods are present like phase parallel, divide and conquer, pipeline, process farm, domain decomposition. We'll try to look into one by one them, right? So very first model comes into picture called as a phase parallel model. What is mean by phase parallel model? In this particular model, basically the complete flow or the complete program is divided into two basically stages, which those two stages may be like repeated multiple times, right? So the first stage is that the computation stage. So you have a problems and you have divide and identify the problems in a such way that okay, you have some, let's say, 10 components which can run parallelly. Then in a first phase which is called as the computation phase, you do only computation, right? So in your like flow, let's say 10 process with you and 10 like subcomponents are there, okay? So now at a time t1 you are only doing the computation. Now once you all those computation is done, then next phase come into picture called as an interaction phase or the synchronization stage, where all process basically stops for some time and they try to communicate with each other. So whatever the data they have with them, they may exchange the data, they may share the results in between, and once they are done with the sharing the results, then once again they will go for the computation phase and then repeat for come to the like interaction phase. So in phase parallel model, basically these two phases are there in the whole execution of the program. So this is one is like very simplest method of doing it. So you maybe like slowly try to relate your problem for the different cases, right? So it may be the possibility that for a given problem there is not only one method may be suitable for you. So it means that if you have the problem, then in the solving from the top to end, in between you may be using one phase, in between that or after some stages you may be using the another stage. So these like different methods maybe fit into a different section of your problem. So here the algorithms or generic methodology which I'm discussing you, so it's like completely depend on like what kind of problem you are going to solve, right? So I hope you are getting uh, what I mean to say, right? So as I was mentioning, in this phase parallel model, basically there are like a different step and all these has the two phases, right? One is the computation phase and another one is the interaction phase, right? And in the computation phase, I was as I was mentioning, all the process at the same time t1 do the computation, and at a like time 2, okay, after some time whatever we have decided in that phase, they all at a time will be communicating and sharing the results, right? So now another like approach comes or the algorithms comes into picture called as divide and conquer, right? So in this particular case, what happens if you have the big problem with you, okay? So at a very first stage, you divide that problem into two parts. Now you keep on dividing the part, okay, till you get the leaf nodes. Okay, so these are, let's say, a leaf node. So first you try to like divide the complete problem into subsections, okay? And at the end you do the computation, and once they do the computation, then try to collect the results to like whatever the parent process they have, okay, and at the end you will be getting the result, like maybe at this particular node, or the like who have like a parent process or the parent node. So this is a basic simple model, okay, where rather than you at the same time you are like making all them in the like computation and all them in the synchronization phase, because that particular like methodology may have a different challenges and may not be suitable for every kind of problem. But in real life, okay, there are different scenarios, or there may be the different scenarios where such kind of situation may be required, right? So maybe like searching algorithms, or maybe things like in real life problem, there are different things where if you want to search your number from an or maybe locate a number, okay, if you have the series of numbers from, let's say, from 1 to 1000, okay, and they are ascending in nature, and you know want to know like what is the location of my given number, okay, then you first divide that array into two, like 0 to 500, and then 500 to 1000, okay, then you check that, okay, in which like section my problem is there, okay, then once again wherever that particular problem like number is there, once again you divide it, and you keep on dividing till you get the result. So this is like there may be multiple scenarios where this particular models come into picture, right? Basically it's nothing but the parent and child kind of the scenario. So parent process divides its workload into a several smaller pieces, right, and assign the like task to the child process, right, and then the child process computes it, and results are merged by the parent process, right? So here all the tasks, basically the computation related task is performed by the child processes, and at the top the parent process combines the result, and the parent process will be having the result with them, right? As I was mentioning, like sorting, quick sort is one of the like simplest example where such kind of things is implemented, right? Am I audible, sir? Hello?
Yes, sir. Sir, you're
Yeah,
audible.
yeah, okay, okay. uh Now another model comes into picture called as a pipeline model, right? So it's very simple, that right, there is a like multiple data streams are there, okay, and now you want to execute all them in a sync in like parallelly, right? So just take an example, like if you have studied the microarchitecture, okay, computer microarchitecture, 8085 or maybe the 8051, then while executing a command for a single cycle of that clocks, right? So how many like instructions will be executed, okay? So this is one of the simple example where the like this pipeline kind of model is implemented. And in real life there may be the multiple instead of the instructions, there may be exactly the task in your program, right, where you have aligned your task, okay, to different pipelines, and in a single go you are actually executing the multiple tasks, right? Like let's say for example in generic way, okay, they like a phase decode execute, these are like very basic stages in the computation, right? But you just try to observe this like cycle 3 and cycle 4. Basically in cycle 3 and cycle 4 you are actually executing, like you are running, your processor will run all these three steps parallelly, like you are fetching, decoding and executing, also phase, decode and execute, right? So once like lag of 2 to 3 cycles is completed, then for almost all cycles, basically your program is executing all these three like pipes at the same time, right? So this is an example from processor, but this applies, okay, to real life problems where we try to take this approach for a parallel processing, right? So instead of performing it on a single task, we try to perform it and give the multiple process, the multiple task, right? These tasks, and at the same time, basically one process is doing, let's say, fetch, another is doing execute, decode, execute. Here just I'm trying to relate it, right? But in real life there may be the, at the same time, like process p1 is doing one task, process 2 is doing another task, process 3 is doing another task, and all of them are doing at the same time, right? So this is a, like, a concept of the parallel, like, pipeline model. And actually it creates a number of process from a virtual pipeline, okay? And continuous data stream is fed into the pipeline, and processes execute at a different pipeline stages simultaneously, as I was trying to explain it, right? So there are like a different processes which are working on a different pipelines, basically to execute many tasks at the same time, right? So I hope you understood concept of the pipeline model. Then another come, like, paradigms or algorithm or approach comes into picture, called as a process farm model. And this is one of the generic model, okay, where like in many places people go for it, because it has a concept called as the master and worker, right? So here what happens, like in let's say you just, as the name it mentions, okay, process farm model. So if you have the farm, and there is one owner for that farm, right? And he may having the multiple workers who are working under him. So the basically the work of the that particular farmer is simple, to distribute what work has to be done by which worker, right? So there is one master, okay, or the farmer, and he has the many workers with him. So the distribution and collection of the results is the only task of this master, and actually the execution task is for the worker, right? So you can just have the, like, very basic difference between, like, the parent and child process as compared to the master. So in case of the parent and child process, maybe the child process may be a parent of some other process, right? So in some scenarios one process maybe play a role of the child as well as the process at the same time. But here what is happening is that all the other processes are actually the worker. They don't have to do any work related to managing and those things. So the master basically sends some task to the one another process, worker process does that particular task, and it only sends that task to the master. So this is like simple, like, model where there is a involvement of one master process, and another involvement is with respect to the other process, which is actually only a computational, handling only computational related aspects, right? So as I was mentioning, master process processes the execution, essentially sequential part of the parallel program. As I was mentioning, like, just understanding the workload, okay, and then distribution of that workload and those things. So once he understand that, okay, what particular task has to be processed by which worker, so that execution basically the master performs in, basically in a sync, like sequential form. And once he knows that, okay, now this particular task has to be given to that person, that particular task has to be given to another person. So all those, like, tasks or the managerial task will be performed by this one single entity. Just take an example of your, let's say, class, okay? So there is a teacher in a class, and he has the 10 students with him. So he has to do some, like, assessment of the papers from the different another class. So if he has to, like, assess the paper, let's say 100 papers are with him, and he just distribute the 10 papers to all this, like, whatever the fellow research fellows he has, okay, or the his students. So all of them will be individually working on this one set of their task, okay. And once they complete their task, they will contact their teacher. So these are the results. Yeah, I have completed it, just get the results or the one seat. And all those ten persons, or all those research scholars, will be working in a parallelly to perform that task fast. So this is like a simple example of the this master slave or master worker concept, right? So as I was mentioning, when a worker finishes its workload, it informs the master which assigns a new workload to slave. Then another concept come into picture, or the scenario comes into picture. We may need to go for the decomposition, like domain decomposition. So there are many real life applications, okay, and the scenarios where basically we need to decompose the problem. Let's take an example of, like, let's say weather forecasting scenario. So now you want to predict the weather of particular region of the Indian content. Let's say I want to predict the rainfall from southern part of the India, which, so when I try to locate that particular region on the map, okay, so I will get something called as a grid, right? Or maybe there may be the different scenarios. I just want to calculate or predict the flood flow of a river, so from which region to which region that particular river flows, okay. So that particular region is basically mapped, or the processing, like whatever the data, local data they have located in some like form of a grids. Or so my target is that, okay, to decompose that particular grid so that I can do a parallel processing on it. So just take an example here, okay. So there is a domain. It may be like either a region of, let's say, southern part of the India. Okay, I just located that particular region, and now I want to like process that model. So rather than like processing that particular model singly or in sequentially, what I will try to do is that I will decompose that bigger grid into a smaller parts. So I will try to decompose like some AP related section from the some Maharashtra related section, some Tamil Nadu sections, or like likewise I try to distribute every uh, like that grid, okay. And I will try to then assign some grid to some number of process, right? So what will happen is that, okay, so on all grids basically my program will work parallelly, and instead of going for the single like process sequentially, I'm working parallelly. So there are different scenarios, okay, where we need such kind of a decomposition methodology. As two real life example I have, I was discussing. One is like the weather forecast, flood flow forecast, and those things. So but in reality there are so many if someone is working on, let's say, fire forecast domain, if there is a way, how you can say, direction my fire is flowing. So I may need to look on priority
Yes, sir.
that particular.
Your presentation
Yes.
is not visible.
uh just pardon. Okay, now is it my screen visible?
Yes, sir. Now it's visible, sir.
Okay, okay. So I hope you understood like the core concept of the domain decomposition. As I was mentioning, okay, domain decomposition is performed with a simple geometrical multi-section approach, okay, where we try to divide a big problem, okay, geometrical problem, into smaller segments, and for every segments we will be assigning some number of like processing units where they will parallelly try to work upon, right? And as I was mentioning, so whenever there is uh, compute units, or problems differential equations, okay, are present, then such kind of scenario or method comes into a handy very easily, right? So basically whatever the like methodologies which we have understood as of now, so these are like a generic approaches, right? So now one may have the question that, okay, for my particular problem, which particular methodology or the approach I should follow? So the answer, as I was mentioning earlier as well, so it's totally depends on like how you have decomposed your problem, okay, and how you have identified your problem into a simple task. In a complete from top to end, you may be utilizing one or more like methodologies in your complete problem. So for some section you are using, let's say, the domain decomposition, or maybe if you have some, let's say, some data to be just distributed and just collect from the, let's say, take an example of weather forecast only. So in the weather forecast, there are like multiple steps. One is to collect the data from the different sensors, okay, like humidity, temperature, or maybe some images from the satellites and those things, right? And then once you have the data, then you become like try to work on that particular data to forecast the rain. Okay, so you can understand that in this particular complete step, in initial stage like data collection and storing and processing, you may go for another approach. And while doing the computation on the grids or maybe on geometry, you may prefer another approach like a domain decomposition. So it's totally depend on like how you are probably solving your problem, right? So generally, by choosing the approach or the paradigm for your problem, there are some of the desirable attributes. So what should we look into? Okay, so one thing is like concurrency. You should be able to identify, okay, the sections where you can perform simultaneously, right? So the data dependency is required before implementing that. Then scalability, look for the scalability perspective, okay. As I was mentioning, resilience to increasing the processor counts. If another large number of processes come into picture while developing your algorithm, you try to like have the aspects that, okay, I should be able to work on like maybe my program should work on 100 or 1000 cores, okay. So many, like I have seen and experienced that many people, they try to hard code their problem for some specific configuration of hardware only, right? But later on what happens, their hardware somehow gets upgraded. If the new hardware comes into their place, then somehow then once again need to rewrite the code, because somehow they have hard coded their problem for very specific architecture only. So now once again he may have to invest that much amount of time and that much amount of resource and money and everything to once again port that application to that. So porting becomes one of the challenge. So if you are working from the scratch on your problem, so you should like have the flexibility from the start itself, so that in future you may not find a problem to work on the bigger systems, right? And while like decomposing the problem, always try to have optimal communication to computation ratio, like ratio. So if, as I was mentioning, like there is one important step in like the whole complete cycle. You identify and decompose your problem and then try to like identify the nodes or the processes which can communicate with each other, okay. So while designing your problem, if you could share the data, okay, whatever the communication is happening on, let's say, with the different process, so that particular process should be nearby to that the original process, so that the communication will not be an hamper. So as we have discussed, as we are discussing in like in real life, the systems are like a shared memory system, distributed memory system. So if you are like mapping your communication in a such way that one process from one node is actually trying to communicate the process from another node, so in that case you can see that there is a path of interconnect one need to follow. But instead of that, if somehow you design your problem in a such that, or map your like communication, instead of going for another node, try to communicate with the core or the process which is there on their node only. So in that scenario, you may reduce the complexity of the communication. and ultimately your performance for your algorithm will be high. So the data locality is also one of the aspect which you may consider while developing your algorithm, right? And modularity, as I was mentioning, decomposing a complex into smaller parts, identify those, okay, as much as you can, so that you will be taking the advantage or leverage of the parallel programming, right? So like just to summarize, like from start to end, okay, what approach one should follow is that, like if you have a problem with you, okay, you just decompose into simple tasks. This very first step. Okay, so you have the problem, you decompose that problem into simple task, and then try to have figure out the communication pattern between them, right? So communication pattern, or maybe like which component is dependent on whom, okay. So basically in a very first step, you just like randomly or like in a vague way, you just identified the different parallel components of your bigger problem, right? Then now you try to identify the dependency or intercommunication between these process, okay. So once you identify that, then just do agglomeration. So agglomeration means that if you identify that, okay, no, I actually cannot like parallel these two models, because if I try to parallel this one, then maybe there may be the possibility that, okay, I am losing the accuracy of my model. So it means that I need to run these sections in sync, like serially only. But at the same time, I can parallelize, like I can run this particular section and this particular section parallelly. So it means that in my bigger problem, there are like some of the sections where I have got some sections of the code where I can like run those on like parallelly. So in this particular case, I let's say I got like say four groups. So then finally is things that then you try to map it to your either course or the threads, right? So you may have like seen the examples, maybe practically you may have seen some of the examples in case of the MPI or maybe the OpenMP, where you try to think about distribution of the workload, to which process or which thread, which portion of my work should be go, okay. So if you have studied the OpenMP, then you may remember that, okay, we just try to decompose or uh, mm, as- as schedule the iterations of a for loop to a different number of cores in case of the OpenMP. Or in case of the MPI, we have seen that, okay, if there is an example of a trapezoidal rule, okay. So basically we were trying to distribute the chunks or the value of yens among the different process to work parallelly. And once you do that, then somehow you try to map that section to different process. So process 0 will be working on from 0 to 25, process P1 may be working on 25 to 50, like that. So mapping is another task, right? So mapping means that then you go for the implementation. So you remember, like you may like have related now that, okay, so if you have the knowledge of the MPA or the open MP, then it's not the case that you should directly go for implementing any problem in that particular language. But the whatever the earlier stages, here we are talking about like agglomeration, communication, decomposition, like from the problem identification to all these steps, one should have like theoretically should be very clear. So once if that particular like algorithm designer have the clear cut understanding of the above steps, then the implementation becomes very easy for you, right? But if you directly switch to implementation, then you will like end up in a mesh, and you may not get what you are desired. So I have seen closely many people who try to write the parallel programs. Okay, they try to take the leverage of the HP system, but they end up in such kinds of programs where they don't get the accurate results, or actually the approximate results which he wants. So there are, as I was mentioning, there are always two things: performance and accuracy. These are the two things we should get out of our parallel implementation. If we are not getting that, okay, and we are not focusing on that, then there is no use of going for the parallelization and those things, right? So these qualities one should have before starting developing or writing a parallel program. That's why actually I had mentioned earlier, basically the parallel programming is a art rather than like a technically writing the code is like a secondary thing. So identifying from the theoretical perspective, identify the problem, decompose it, make the proper communication, just then try to map it. So the final stage is nothing but coding and mapping and those things. So I hope you understood. So like when we try to like think about, just to check like in generic sense, what is the like program flow of the serial to parallel is nothing but like that. In case of the serial program, what happens, the stages comes like if I just want to summation from 0 to like 1 to 10 raised to 19, so this is very big number, right? So if I want to calculate it serially, so what happens that just start the program, provide the input and do the computation one by one, just add 1 plus 2 plus 3 plus something till 10 raised to 9. And once you do that, then provide the output. But what actually happens in case of parallel and what we expect is that, okay, these are the things, like we just started the program, okay, then we provide the input. So we just replace this do computation, this task first into like dividing the work and create the communication pattern between them, okay. So this one step, and once we like divided the work among the process, then do the process like that computation parallelly. Here we do the parallelization, right? And then finally try to collect the result. So you can see that the here in this test do parallelization things like like methods like the actual programs like MPI, OpenMPI and those things come into picture. But for doing this communication and taking the results back, okay, from to whom I should distribute the workload, from whom I should take the results. So for that particular section, one require bit understanding of that their domain, bit understanding of the problem, right? So if you are like a domain expert, then you will be the good parallel programmer. But you cannot like expect a like programmer to write a parallel program for you if he don't know about the domain. So that's why in like our field, HPC field, basically many says that, okay, that the combination of the data like domain scientist and who knows the knowledge of the this HPC and those things, that's the actually the deadly combination which is having the very large demand in the industry. You take up any sector and you will find the demand for such kind of like resources. So I hope you understood what exactly happens, right? Now when we talk about if I let's say then the now the scenario comes, okay, where I have written a program here. Let's say, for example, by using some of the methodologies which we have discussed earlier. So one have written a program, right? So now next question comes into picture. I want to evaluate that program, right? So if I want to evaluate that program, then how I can evaluate? So for that, there are some of the matrices. So the very first matrices comes into picture, that is called as the speed up. So we need to check that, okay, whether my program is giving me a speed up or not, whether I'm getting the performance out of my program or not, right? So if I am getting the performance, then we can say that yes, I have done a good job. If I'm not getting the performance, if let's say serial program is taking 10 minutes of time and my parallel program is taking 10 minutes or more than 10 minutes time, then there is actually no use of it, because in that scenario we are using the resources, but if I'm not getting the less time, then there is like a double disadvantage for me. I'm using the resources but not getting the performance. That's a bad idea. So the very first thing, one desirable attribute is that one should get a speed up out of your program, right? So if I want to check the speed up, then this is like a very simple for mathematical formula. Just divide the sequential time for which was taking by the sequential code divided by the time taking by the parallel code, right? So, and this speed up may be like lies between the one to uh, like number of process which we are using, right? So this is like, and we will try to see some of the real life mathematical formulations by which we can calculate the speed up and those things, right? Then another parameter matrices come into picture, whether regarding the efficiency, right? So though you got some speed up, but with respect to whatever the resources you are using, are those like efficiently you are using or not, right? So that thing we can calculate it by like speed up divided by number of process. If I do that, okay, then I get the speed up, right? And speed up is equal to 1. It means that whatever the number of process I'm using it to like very efficiently, 100% efficient. So this is like a very ideal scenario and the situation, right? So these are the two like basic level parameters or the matrices where you can choose for checking uh, your programs which you have written or developed. Now if I want to calculate, I was as I was mentioning, so this is like simple like mathematical formulations of the speed up and those things, right? So as I was mentioning, speed up is one of the important aspects for the matrices for parallel programs. Okay, so what are the like different laws for it? So the very famous and fundamental law to calculate the speed up, okay, is given by Amdahl's, okay, 1970. Basically he has stated that, okay, if you keep the problem statement same and you try to increase the number of process, so that scenario he had talking about, okay. So what you stated that the speed up of your program using multiple process is limited by the time needed for the sequential fraction of the program. So it means that, okay, let's say you have a program which is having, let's say, 20% of sequential part and 80% of your code can be parallelized. So 80% of the section of your program are like in a such way that they are independently executing the task. So those many sections of your code you can do parallelly, but still there is some portion of your code like a 20 or 10% which anyway need to sequentially execute. So what the Amdahl's law says that, okay, though today you are, let's say, using it, let's say, 8 cores for those 80%, if you tomorrow you come up with 16 or maybe hundreds of cores, but anyway your speed up is not going to go beyond that 20%. So this is what actually he was trying to say. Speed up is basically limited by the sequential part of your code. So just take an example, as I was mentioning, if there is a code which is having the 10% in serial in nature and 90% parallel in nature, okay, and we try to run this particular core on 10 processors, okay. So in this case what will be the speed up for this scenario? So you just try to put the values in this formula. N is equal to 10, where number of process we are talking about 10. Then the parallel portion of your code is 90, like 0.9. Then 1 minus parallel where the 10% code is a serial. So we just try to put those values, and we get in this particular scenario for 10 number of process, I will get speed up is equal to 5. So you can see that by assuming like getting this score, like using this particular law before actually executing your code on your hardware, if you know that, okay, this is my like if I have the code which is having, let's say, xyz x% of serial in nature, and then y% in uh, like parallelizable. Okay, then what will be the speed up for my case? So if you know that theoretically, then you will be able to identify that for your workload, for your current like program, what kind of system I should go for, right? So here, let's say in case, in the same case, if instead of 10 process I use 100 or maybe 1000 process, but you can see that, okay, I cannot in any case for this particular problem, I in any case I will not get the speed up more than 10, right? If I put the infinity in this particular formula, right? So 1 divided by this particular, like 1 divided by 1.1, and this entity will be 0. Okay, in that particular case, speed up, maximum speed up possible is 10 only. So basically what Amdahl's has stated that, okay, here we are actually not uh, varying our problem. Okay, for a given problem, for such scenario, for given algorithm, okay, how many my program will efficiently work on how many number of process, or how many number of processes I will be required to get maximum performance out of my program. So that aspect has been provided by these amdols, right? So in essence, basically amdols was trying to like tell the limitation of this parallel processing for a given parallel program, right? So that was one like what I can say approach the people and the scientists were looking for a parallel processing and the parallel like architectures, right? Then later on, when another like man come into picture, okay, Gus Thompson's, okay, uh, as till like 1988. So basically, the industry people who were manufacturing the multi-core and those systems, they were somehow like having the doubts or question on manufacturing of these multi-core processors, whether we should go for it or not. Because if there is no problem, if there is a problem where problem itself uh, provides the limitation on going for the like parallel architecture, then there will be no use of manufacturing those like hardwares, right? But later on, when another like this man like Gustav Sons come into picture, who actually redefined this term. Okay, so what he wrote that uh, any application can retain a scalability on large number of processes by increasing the problem size. So here we were trying to say that, okay, the problem was fixed, right? So problem was fixed, but he has told that don't look for the like one problem. If you increase the problem, don't put the problem like constant, but if you increase the problem, okay, then you will get the benefit of large number of processes. So this was one aspect. Basically he has given one another vision to look into the speed up. So he has given the different formula for the speed up. So remember that, okay, the formula speed up, if you use the amdols, or maybe if you use the like this custom sense for this, the in both scenario the speed up will be a different, because from there how redefined actually the speed up term. Okay, where he has uh, like provided another like approach where he stated that, okay, if I increase the my problem size, okay, then certainly I will get benefit of the underlying parallel systems or parallel architectures. If we have the big system, so instead of running one problem on those system, if I increase the problems or number of problems on my system, then certainly I will be able to take the advantage of that particular system. So once he published the articles on the paper, then once again the industry people, manufacturing companies started working, okay, on or developing the multi-core processors. Then parallel machines come into the picture, parallel systems. So after 1919, if you just check up the supercomputers history, okay, after 1990, okay, basically the parallel processors and the HP systems, big supercomputers which were using the parallel machines, has been adopted by the like industry. Okay, so this was one of the another approach which this Gustafson's law has provided, right? And actually he like whatever the Abdon's law has provided this equation mathematically, okay, from the scientific domain, okay, so he actually like overcome the shortcomings of the Amdahl's law, okay, and he actually told how one can fully exploit the larger computing system which when they have. And this is actually now in the current scenario on all systems, this paradigm or this approach is has got accepted, right? So, as I was mentioning, she actually redefined the term speed up, right? So, if you just want to like what exactly the difference between the Amdahl's law and the Gustafson's law, just take an example of like a transport company. Okay, so what Amdahl's law was trying to say that if there is a one truck with me for the transportation, I cannot load any number of like load like a large workload on a single truck. So certainly there is a limitation for it because he was considering only a single truck there. Okay, problem is same, but what he says that the customs law, so why are you you're trying to use only one truck? Let rather than that think of like distributing that particular work bigger workload on the multiple trucks, and in that particular scenario you can be able to like cater the bigger problem. Okay, so basically this another approach this Gustafson's law provided, and that was then accepted by the community and the people were starting working on it. So as of now, anyone having any question? If you have the question, then please you may type into the chat, right? So as of now, I just to recap what we have discussed as of now. Okay, so we studied upon if one wants to write a parallel program, okay, so he should not directly go and implement that by using any of the methods which you have learned as of now. So very first thing is that you should understand the your problem optimally, try to make the patterns, and then try to identify which particular problem will be useful, like which particular algorithm will be useful for your problem, right? Once you identify it, then try to go for implement. So once you implement that, okay, then evaluate that by some of the matrices, right? So like the speed up and the efficiency, and if you want to calculate the speed up, okay, then these are the things, because anyway if you are writing your developing your program, so in that particular scenario, and you may use the Amdahl's law just to identify that what number of resources will be useful for my scenario, right? So there are like I have seen many developers who develop the pair program, or maybe like professors or the small scale industry people, they ask a question that, okay, if this is my problem, then what should be a size of the machine which requires for my problem to solve. So this is like a very close problem. So for such scenarios, maybe Amdahl's law useful for those scenarios, right? Because you have a complete one problem with you. You are not talking about the multiple problems, right? Or you are also not talking about like a very big problem from that perspective, right? So you know that okay, this is my problem, okay, and for that particular problem, what should be the system sizing? Okay, so in that particular case, just try to identify the parallel portion of your programs, serial portion of your program, then try to put the values, and then you can like approximately get a fair idea. Okay, for solving my problem, I may require this size, this much size of the system. Because remember that okay, in like HPC word, resources is the very scarce thing, right? And many people, like if you have explored like a Google Colab or maybe the Amazon clouds, okay, then you may have like realized, okay, if you choose number of resources, okay, and as you increase the number of cores, okay, your billing will increase in that proportion, right? So before asking some number of cores from the either cloud or maybe from your like whoever the resource provider you have, from the domain perspective you should be very clear that okay, for solving my particular problem, I want these many number of cores, or I want this particular resource clearly. So that in that scenario you will be using like optimizing two things. One, you are optimizing the resources, okay, and then you are optimizing your like money and financial aspects as well, right? So now, as I had came to for the optimization, okay, so I will just like briefly touch upon what exactly the optimization means, right? So you have seen this particular diagram, right, in our like execution. So in our scenario, okay, so certainly the resources is like a very scarce entity and very important entity. So as I was mentioning earlier, I should optimally use those resources, right? So now when I talk a word like optimally, so what exactly it means, right? So if I have problem with me, okay, and I want to run that particular problem on my computer system, so the my question is that is my program actually optimally using the underlying resources or not? So just at this moment, just forget about like underlying parallel systems or those things. You just focus on let's say this single core system. Okay, if you have written some program, okay, and you want to use this single core. So my first question is that whether my the same like program is optimally at least using this single core or not. That is one question. Okay, when I know that okay, now my program is actually utilizing this course optimally, then I will go for like multi course or maybe another course with me which are available, right? So this approach is actually very essential and important. So I have seen and experienced many programmers or the people who write the codes, okay, they don't uh, think about like they says that okay, if I have the machine then I will directly go for it, parallelization and those things, so whatever it. But certainly there is a scope of like optimization, and here in our like day-to-day life work, okay, we try to optimize those things. So many people and codes they don't look into aspects while implementation. But if you have the approach and the knowledge where which sections one should look into, then from the start itself your code will be very efficient in nature, right? So as I was mentioning, okay, let's try to understand this aspect practically. I will try to show you some of the demos of how like those like, things uh, uses, and while like simply making some changes in the compiler flags, you can get the optimum performance, right? So before I switched on to the like demonstration, okay, let me tell you couple of things here, okay. So the first thing is that we have hardware with you, so everyone agrees on that. So in previous sessions you may have understood like the importance of the hardware, multi underlying hardware and those things. So now also one another important thing you should understand, that though we have the advanced hardware, along with that we also have some of the very good advanced compilers, advanced software stack which are situated on your system. Along with the hardware, advanced hardware, there are like advanced compilers or advanced software stacks are also available. So the now question is that are you aware of it? Because like updating and using the software components, making the changes is very easy as compared to replacing the hardware and those things, right? So from the programmer's perspective, anyway, here you are writing the programs, it means that you are creating a software, right? So the question comes into picture whether you are like using those hardware like compilers features and those things optimally for your program. So that is one question. So now for like as I was talking, okay, optimizations comes into the multiple levels basically. Okay, so one level is like compiler level optimization, that comes into like very first thing and very handy. Okay, of which we will be talking about in the demonstration. So that comes like at a compiler level, right? So another level comes into picture with regarding the optimization is the libraries level. So uh, in open community there are like so many things, okay, like basic calculation like matrix calculations or like linear algebraic calculations. So already some of the people optimally have developed the algorithms, okay, and instead of you implement those once again, okay, just try to use those library into your program, okay, and then get the optimal performance. So if you try to implement the like matrix multiplication, okay, or maybe like algebraic equations, write those programs instead of that, okay, you use the already implemented. So integration of the libraries into your program, that is another level of optimization, that is called as the like library level optimization. So this comes into picture when you are working on real life applications, either you are working on any domain of your choice, then that library level optimization come into picture, right? Then third level of optimizations come into picture, which is called as a source code optimization. As I was mentioning here, like, and in the same lecture, we were trying to discuss about developing the algorithm, making the changes in the algorithm, okay, which method will be good, okay. If let's say someone has implemented one method, but you identify that, okay, that particular method is not optimal for this particular scenario, then you directly change the source code itself of that particular program. Okay, so that is actually called as a source level optimization. So these are like some of the like aspects where optimization terms comes into picture. Okay, so here I am going to show you some of the aspects regarding the compiler level optimization. So very first level of optimization, which is a compiler level optimization. So just to confirm, I have just switched the screen. Are you able to see it? Hello, can anyone please let me know whether I am my screen is terminal now and are you able to see it?
Yes, sir. Your terminal is available, sir, now.
Okay, okay, thank you.
It's visible.
Okay, so as I was mentioning, due to the time constraint, I have just took the optimization for the compiler level. Okay, so we'll try to discuss it and how actually it helps to get the optimal usage of the program, right? So let's say for example I have just logged into one of the like supercomputing systems, okay, under nsm, okay. You may also having access of it. Let's say I have one program, matrix, simple matrix multiplication program with me, okay. This is simple matrix multiplication program implemented where I have just uh, written some simple code, okay, where I'm just doing the matrix multiplication, where I have initialized this particular matrix, okay, and then doing the matrix multiplication. Here the matrix size is, let's say, 5000. Okay, so this is simple matrix multiplication program, right? So now if I want to compile this particular program, so generic like method, we just provide like a something ICC, okay, and then provide the flags, and then we'll try to see it, okay, and then we run it. So now when it comes for the optimization things, from the compiler perspective, there are multiple stages, like, and those stages can be specified with the keyword O. Okay, this is the O keyword. So let's try to start from the first. Okay, so first thing, like, here I'm using the ICC compiler. So you may be, as of now, you may be aware that on any HP system there may be a multiple compilers available by the different vendors. Okay, so the GCC is one from the open source. Okay, open source. Then ICC is a compiler given by the Intel. Okay, so if you have the Intel compilers with you, then the ICC is there. Okay, so here for this particular program, I have set up the environment. Okay, regarding the Intel. Okay, so for this particular program, I will be compiling my program with Intel compiler. So ICC, okay, then I just specify a name of the output binary with small o. Let's say I specify it as a serial, okay, serial, maybe, or let's say okay, matrix multiplication program. Then let's say I'm not giving any optimization level here. Let's say I don't give anyone. Okay. So if I don't give anyone, it uses basically the O2. Okay. And then the name of the program. Okay. So this is a simple one. Okay. So if this is the compilation level. Okay. And here I'm giving an optimization level as a O2. So if I want to go for the O2 level optimization, then I need to pass on this flag. Okay, so hyphen O and 2. So level, I'm telling that, okay, optimization level as a 2. So this level basically starts from 0. Okay, so 0 means that, okay, we are forcefully telling the compiler that don't do any backend optimization. So optimization means that at the backend, our compiler basically try to by default do some optimization, like if there are loops, okay, unrolling of the loops, then like trying to make that loop properly so that it will get executed in a pipeline mode or vectorization, those things our compiler, like advanced compilers, will try to implement it. But when we try to say that, okay, don't do any optimization, then that level is referred as a hyphen o 0. Okay, the next level is that o1. Okay, so here we say that, okay, just try to do like very basic level of optimization. Let's try to implement some rolling, loop unrolling, and whatever, like the underlying features are there from the compiler side. Just try to do that, but don't do an aggressive uh, like optimization. Then level like o2 level tells like, okay, try to have as much as possible optimization. Okay, so from the compiler's perspective, try to do as much as possible from your end. Okay, but if there is some ambiguity in the code, so don't do that. Okay, and in many cases like this, every compiler sets some by default level of optimization. So in like in case of the these like nowadays standard like level of optimization we have for every code is o2 level. Okay, so here we'll try to compile our code with O2, and there is let's say then the final level is called as O3. We will try to see the difference between the O2 and O3 anyway, and then certainly we'll like you can imagine the difference between the earlier stages of it. Okay, so let's try to compile our code with this. Okay, then you can see that here this O2 whatever we have written, so we have just uh, compiled and I got it. So I run that particular program. So this just remember that, okay, this is the serial version of the program, right? Then I go for it. Okay, and now this particular program is running. Okay, so if I want to check that, okay, whether it is running, then I will just switch the terminal and you can see that, okay, if I just fire a top command, then you can see on my system, okay, there is one executable is running with this particular user, home user, and actually it is using the one core 100%. 100%, it means that actually it is using one core with the fullest, okay, capacity. But still, here we are hard from the hardware perspective, we are using the hardware 100%. But my question is that from the compiler perspective, are we doing the high level optimization or not? We'll try to see that. Okay, but here you can see that, okay, now our code is actually running and which is using 100, like one core. And if I once again go deep into it, then you can see that there is one core like CPU 0. Like on my system there are like so many number of cores are there, okay. But earlier that CPU was like that, my program was using one. But I think the program has completed now, then the utilization has stopped, right? And you can see that my program has completed in 18 to like 56 seconds, right? So now I will try to once again compile the code, okay. But here I will try to use as a o3, okay. And let's see what happens, okay. So now you can see that, okay, now this o3 has been there. Now I will try to run the same program with this binary, right? And now in this particular scenario as well, you can see that now this CPU1 has started using and CPU1 is utilizing 100%, right? So here you can see that we are using the hardware, okay, with the single core, and actually it is running for some time, right? So here you can see it, right? Now let's try to see how much time it takes, okay, to do the computation. So you can see that we are not changing any program, we are not changing the hardware and those things, rather than we are just change the compiler flags here. So you can see the results between the time taken by the O2 and O3. So you can see that, though I actually for the demonstration purpose, basically I have taken a very small size, matrix size 5000 by 5000, okay. But with that as well we are able to, but in reality there are like so like hundreds of thousands of matters maybe there in, and we want to solve it. But you can see the difference here. So if I'm just using the O2 flag here, okay, where yeah, execution time was like 56 seconds, approximately 1 minute. But if I go for from O2 to O3, then my time has reduced drastically from 56 to 50 to 37, almost 20 seconds performance or improvement I got, right? So what changes I have done? I have not changed the code, I have not changed the hardware, but I just did like some compiler level changes and I got the performance. So why I'm trying to show you here is that many people don't focus on these. So two things, like they either they don't know their hardware has upgraded, also they don't realize that their whatever the softwares they are using, those has also got some intelligent features with them, right? So likewise you can like see the difference, right, by using the optimization. And you can see that if you just try for the lower level of like optimization like level 1 or 0, then this execution time will certainly increase in that proportion. So due to time constraint I will not show you that. But one last thing I just want to show you here, maybe within a couple of minutes we'll try to wrap up the session, okay. So one thing, like though we have seen the way this serial program, right, but in case of the openmp program you may have seen the like multiple cores and those things, right? So with the serial program we were using like getting the optimal performance like a 37. So if I want to once again gain the performance, then I have the choice for going the parallel implementation of it, right? So I just taken, just for the demonstration I've just taken a one simple openmp program which works on the same size here, same matrix multiplication program, same everything is same. I just implemented it into the openmp. So if you have studied the openmp, you know that what is the meaning of this particular line here, right? So if I try to run it and let's say I'm using the 4 cores, okay, for this one, then I will just first I will try to set the environment omp, okay, num threads is equal to, let's say, 4 threads I set, okay. And then I just compile this particular program. Okay, once again icc hyphen o3, whatever the like optimized for the single core I have got it, let's say I have taken it. Okay, then q open mp. Okay, then I get a name like mmomp something output name I have given, and I am using it. So this is the way by which I can compile my OpenMP program, right? So let's say I compile it, then you can see that this OpenMP has got. Now with this code I am just using running it, right? And here you can see that okay, now in this particular case it OMBMP open running and it is using 300 or 400%, or maybe in between you can see that a 1 2 3 some like these CPUs where actually my programming was using at the end backend, right? So it means that in my case, in this particular OpenMP case, instead of using one CPU, my program was using the four CPUs. And if you see the timing difference, 13 seconds. So what you understood here and what I want to demonstrate to you here, so first go for trying to see like whatever the serial resources or whatever the resources which you have, just try to software by using the software advance and those things, you just try to make optimization of it. So once you have done that, then try to look for the if once again you want to have the optimization or like gain more performance, then try to look for the another parallel programming models like OpenMP, MPI. And when you are exhausted with like one single machines, then try to go for like multi-distributed kind of system like implementing MPI, the accelerated things and those. Okay, so I hope you understood what I am meaning to say. So just to come back on this slide, so I always show these slides in my sessions where I encourage the people just to realize that okay, two things like underline either you know it or don't know it. Okay, that your systems has been upgraded as well as the softwares has been upgraded. Now it's a time to upgrade yourself. Okay, to utilize those systems efficiently and parallelly. And once you are aware of it, then you should be able to ride a systems like high performance computing system, HPC systems, with your knowledge set, okay, efficiently. So that's actually our target, okay, for your explorations. And if you could have gained those knowledge in the this like whatever the duration of these 5 days of work FDP program, if you could have gained that knowledge, then that will be the like essentials and benefits of it. Okay, so that's it from my side. If anyone have any questions, then we may go for the questions for a couple of minutes. So I hope I was able to come and complete it on the time. Yeah, it's good. So if anyone have any questions, I will be happy to answer you. So anyone?
Yeah, dear participants, if you have any questions, please post
Yes,
in the chat box.
yes. So that's it from my side. Thank you very much. I will be looking for the charts. Okay.
Thank you very much, sir.
Yeah.
Found no questions
Yes.
in
Thank you.
this session, and thank you very much for your enlightenment session. This is the second session from you, sir. So there is a tremendous response from the participants in our participants group and then in on my personal chat. So really, the people wanted to have live hands-on sessions from you, and then
Sure.
we definitely plan in future to have your physical sessions at our campus, sir. So once again, I really thank Om sir for his uh, commitment to deliver these sessions and then make this program a grand success and then benefit the participants at maximum. So once again, thank you very much, sir.
Yeah, thank you very much. If anyone have any questions, you can reach and you may share the things with me so that I can help you out.
Yes, sir. I'll share your mail with them, sir. If anybody have any doubts, they'll be reaching you through mail.
Yes, sure. Thank you. Thank you everyone once again, and all the best for further sessions. Yeah. Thank
Thank
you.
you very much. Thank you, sir.
Thank you.
Dear participants, we have see we are on time, and then we are about to start the next session from the Vamshi sir. I request if you have any doubts, you can just share the doubts in chat or in WhatsApp group. We will definitely share these queries to the resource persons, and then post the answers even in the group and then mails. Thank you very much. Murthy sir. Murthy sir. Session feedback is shared in the chat box. I request everyone to please provide your feedback on the session. Murthy sir.